Okay, our next topic, or section in this topic, 2.2, is horizontal motion. So something like this could occur where, say you have a tree, then the tree represents where x is equal to 0, and you have a car, say at x equals 2 meters, it picks up and drives, oops, 2x equals 10 meters, and that would be driving in a positive x direction. But starting at the tree where x is 0, you could also go backwards, so it could be in the negative x, or it could go, from 10 meters and turn around and go back to 3 meters, and your change in position would be negative for that. So motion parallel to the ground is considered horizontal motion. And we're only interested in the one dimension, so we'll call this the x-axis. Later, we'll do x and y. And in a sense, these are simplifications because we're going to ignore some friction effects and things like that for right now. So unless it's stated, we just assume frictionless, okay? Or that the friction was already incorporated into the problem. Okay, so really the best way to get at this, you already have the formulas stated from the previous section, is just to really start a problem and look at some examples. So, here's an example. When the light turns green, a stopped car accelerates forward at 6 meters per second squared. Fully describe the car's motion over the first 5 seconds. Okay, so we're going to use, to do this, we're going to fill in a really good chart. And I have the red for vector versions, but again, we're only in one dimension here, so it's really just plus minus that we're concerned with. Some things in here, it's a stopped car, okay? So that tells us that we're starting at 0. So I always like a little sketch myself. It's good practice. And I write in some things. VI equals 0. It's accelerating 6 meters per second squared. It's going to go to a new point over here where it's moving. We don't know what the VF is, but we know that the time that it gets there is 5 seconds later. That's the one we're going to be interested in. Now we can put in some of this stuff into our chart. This is 0 meters per second. We don't know VF. We don't know average velocity or average speed. We don't know the change in speed. We know acceleration is 6 meters per second squared. We know our delta t is 5 seconds. So let's solve for some of these things now that we know that information. Well, I know by looking at A and T and the formula for A, which is delta V over delta T, that I could rearrange that for delta V and solve for that. So plugging in 6 meters per second squared times 5 seconds, I can see I get 30. One of the seconds on the bottom cancels meters per second, and that makes sense for a change in speed here. So now I solve for that. Now if I have that, I can use the formula for that here, because delta V is Vf minus Vi. So 30 meters per second, I don't know Vf, but I know Vi is 0. So Vf is also 30 meters per second. And I could plug that in right here, solved. Now average velocity, I know its formula is Vi plus Vf over 2. So 0 plus 30 over 2, and that gives me 15 meters per second. So I could plug that in here. Now, delta S, we can come back to the V bar equation, the other one, which is delta S over delta T. Now that will mean that delta S is V bar times delta T, wouldn't it, if you bring the delta T up? So our V bar is 15. Our delta T is 5 seconds. 15 times 5 is 75 meters. So that will go in here. So we fully analyzed that this car that started at a speed of 0, went up to 30 meters per second. So its average velocity was 15 meters per second. Its change in velocity was 30 meters per second in the positive. That gives us an acceleration of 6 meters per second squared over 5 seconds. It traveled 75 meters. Okay, good. So let's go on and continue this with a second car. So a second car. In the adjacent lane to the first car. Was actually timed just right. So that she approached the light at constant speed. And kept going as the light turned green. By the end of the 5 seconds, two cars are again juxtaposed right next to each other. What is the speed of this second car? Okay, well, let's get out another RGC. So in this case, this car, the woman's driving, has an initial VI. We don't know what it is, but it's moving. It's not accelerating, so accelerating is going to be equal to 0. Our time's going to be 5 seconds again, and it's going to be the same speed as it goes at, we actually know, 75 meters again, because it's going to go the same distance as the first one. So we know that this is 75 meters. We know this is 5 seconds. We know this is 0. We don't know VI, VF, V bar, delta V. Actually, if VF is equal to VI, we do know that delta V is 0. And these VI, VF, and V bar will all be equal. So we just would simply use V bar is delta S over delta T, 75 meters over 5 seconds. Or 15 meters per second. That would mean that that's 15 meters per second, and that's 15 meters. So now we know that that car, she was driving at 15 meters per second. The first car started at 0, went to 30 meters per second over that time. They had the same average speed, though, of 15 meters per second. So let's look at another example. An airplane lands with a speed of 60 meters per second. And as a braking acceleration, slowing down, of 7 meters per second squared. How long of a runway does this plane need to land on? Okay, so we have a plane coming in for landing. And it's coming in with an initial speed of 60 meters per second. It's going to slow to 0 meters per second because we want it to stop. acceleration is minus 7 meters per second squared since it's braking. We're interested in how long the runway is. We're again going to use our really good chart. So let's fill in our information. Our initial speed is 60 meters per second, and our final speed is 0 meters per second. Okay, so we know initial and final velocities or speeds. We know the acceleration. And that is it. So right off the bat, you can get your average speed using VI plus VF over 2, and or 60 meters per second over 2, 30 meters per second. We get our change in velocity of VF minus VI. 0 minus 60 meters per second is minus 60 meters per second. Okay. Then we could take our acceleration formula and solve for delta t. To rearrange that, if I brought up delta t, I would get delta t times a, delta v. Then if I divide by a, I get delta t is delta v over a. Important to be able to do those work, so press pause and rewrite that and do that calculation, do this manipulation of the formula so you understand it. But delta v is minus 60 meters per second, and a is minus 7 meters per second squared. 60 over 70, or 60 over 7 is 8.57. Now, meters per second over meters per second squared is the same as meters per second divided by meters per second squared, which is meters per second times, flip it, seconds squared over meters. So we see the meters cancel and one of the seconds cancels, and that just leaves us with 8.57 seconds, and that makes sense for our time, doesn't it? Now that we know that, we can calculate what we wanted to find, which was our delta S, because we have V bar is delta S over delta T. So delta S is V bar times delta T, which is 30 meters per second times 8.57 seconds, or 257 meters. Well, point something, so you better make it 258. If you want to make sure the plane has enough space to land. Okay, good. So let's look at another example now. In this example, we have a car at a racetrack. Starts from rest. And accelerates forward. At a constant rate. 12 meters per second squared. How long will it take the car to travel 50 meters? Okay, so a race car. Okay, so our race car starts from rest, goes down the track, an acceleration of 12 meters per second squared, and a distance of 50 meters. If we look at our chart again, plug in what we know. Let's see. We know VI is 0. We know our acceleration is 12 meters per second squared. And we know our displacement, or distance down the track, is 50 meters. So when we look at this, we could say, well, if to get V bar, I need delta S over delta T. That's not going to work. I have two unknowns. Delta V, I need VF minus VI, so I can't get that. So I'm sort of stuck. The equations I have don't work, so I need bigger, better equations, or bigger equations, maybe not better. And in class, we'll derive these, but right now I'm just going to give them to you, other equations. And the equations that we have are VF equals VI plus A delta T, delta S equals VI delta T plus 1/2 A delta T squared. VF squared equals VI squared plus 2A delta S. So 3 more equations here. Do you have to put into your memory? Maybe make flashcards or something for them. Now the final velocity equals initial velocity plus A delta T. Again, we have 2 unknowns, so that's not working for us. Delta S equals VI delta T plus 1/2 A delta T squared. Would that work? That might work for us. Let's try that one. So if I try this one, I would have 50 meters equals 0 times delta T. So that goes away. Plus 1/2 12 meters per second squared delta T squared. So 50 meters equals 6 meters per second squared times delta T squared. Divide by 6 meters per second squared. Divide by 6 meters per second squared. 50 divided by 6 is 8.33 seconds squared. The meters would cancel. Is delta T squared. Then take the square root of both sides. That would leave us with delta T. And the square root of 8.33 is 2.89. square root of second squared is just seconds. So 2.89 seconds. Okay? Now that we have that, we could also solve for other things, like I could get delta V from A is delta V over delta T. So delta V is A delta T, which is 12 meters per second squared times 2.89 seconds. Or 34.6 meters per second. Since VI is 0, this is 34.6 meters per second. And then average velocity would just be 0 plus 34.6 meters per second divided by 2, or 17.3 meters per second. Great. That ends 2.